Hi, welcome. I'm Professor G teaching you physics. In this particular lecture, we'll be talking about linear motion, and the topic that will be covered is average speed, instantaneous speed, velocity, acceleration, and free fall. So, to start out with, a fun fact. Did you guys know Galileo actually died in the same year that Newton was born? It becomes more important for us to talk about Galileo because Galileo developed the early interest in motion. He described the motion with respect to something else. So before Galileo, people would just describe the motion as, how fast or how slow. So when Galileo came, he actually defined the speed. So he said, speed is defined as distance an object covers in given time, right? So this is our average speed. So when we talk about speed, we are actually referring to average speed. So average speed is the distance an object covers in a given time. So in equation form, our speed becomes distance over time. Precisely, this is our total distance, right, over the time interval given. So let's say I have a train which covers 70 meters in 2 seconds, right? So if I have to calculate speed, then this would be 70 meters over time, which is seconds. So then we'll come up with 35 meter per second as the average speed for the train. Units for speed is meters per second, which is super important. So every physical quantity is actually described by a unit. So speed unit is meter per second. So let's take another example for average speed. So let's say, we have an object, that covers 420 kilometers in, let's say, 2 hours time, right? So if we have to calculate average speed for this, so that would be 420 kilometers, the total distance covered by this object in total time. Total time is the given time that this object travels, so that would be your 2 hours. So final answer, the average speed would be 210 kilometers over hour. So that would be your average speed for this particular object. Now we are going to talk about instantaneous speed. Instantaneous speed is different than average speed. So instantaneous speed is that speed that the object is moving in that given instant of time. Let's take an example. Let's say you're driving on a highway, and as soon as you get on highway, let's say at 11 o'clock, right, 11 a.m., you're driving at let's say 50 miles per hour, and then you kind of speed up a little bit more. So at 11:05 a.m., you're traveling at 55 miles per hour. At 12:05, right, p.m., you are traveling at a little bit slower speed on the ramp. So let's say 30 miles per hour. And then you come to a stop. There's a traffic light. So you come to a stop at 12:10 p.m. And then when I say stop, your speed has to be 0 miles per hour. So see how we have listed our various speed according to the time, right? So this is definitely time related. So your speed at 11 a.m. was 50 miles per hour. So this is your instantaneous speed. Instantaneous speed, the speed that you are actually traveling at that given instant of time. So 50 miles per hour becomes your instantaneous speed. Our average speed, on the contrary, was total distance over total time that an object takes to cover that distance in that given time. Let's talk about velocity. So velocity actually combines the ideas of speed as well as the direction of motion, or an object which is moving at 40 miles per hour with a direction, right? So north would be the direction. So this is the magnitude, and then this gives us the direction. So velocity is a vector quantity because it has both magnitude as well as direction associated with. There are two special cases of velocity where velocity can be uniform velocity, or velocity can be changing. So it has to have both constant speed as well as constant direction. That's when we can call this as a uniform velocity. Now for changing velocity, there are three different factors that we actually look at to call this as a changing velocity. For changing velocity, speed can change, or direction can change, or in some cases both can change. Okay, so let's take a special case. Let's look at circular motion. So here is a circle and we have an object of mass m, which is actually tracing a circle in counterclockwise direction. This is called as uniform circular motion, where speed does not change, but direction is actually changing. And then when we have speed which is constant, and then direction which is changing, so velocity changes, and that brings us to acceleration, the next important physical quantity. Now how quickly velocity changes is what we define as acceleration, is the change, right, in velocity in given time. Right? So let's look at the equation form. So we have acceleration. Again, acceleration is denoted by a letter A. So you have acceleration, which is in equation form. So this is going to be your change in velocity, right? Change in velocity over change in time. Okay, so this we use delta symbol. Delta means change. So delta V over delta T. So I'm going to make a note here for you guys. Delta means change. Okay, so delta V means change in velocity. Delta T means change in time. Okay, so now we come here, and then for change in velocity. So this would be your final velocity minus initial velocity over final time minus initial time. So let me move this equation symbol to here. So this is your acceleration in equation form. Now VF stands for final velocity. It becomes more clear for you guys when I take some examples to work on in few seconds. So Vi is your initial velocity, where the object starts out with certain velocity, and that's your initial velocity, and an object reaches some velocity after some time, so that would be your final velocity. Okay, so TF, T subscript F, stands for final time, and then we have initial time for TI. All right, so we have the equation, but then now we have to come up with a unit for acceleration, right? So physical quantity is not complete without a unit, so we have to come up with a unit. Okay, so I'm going to go back here. So I have delta V, right, over delta T as a part of this equation here, correct? So I'm going to bring this forward here. So what was the unit for velocity? Velocity unit was, what was it? Go ahead. Meter per second, correct? Over, what's the unit for time? That would be seconds. Yeah. Okay. So now look at this. This is a fraction of a fraction. So I hope you guys are good at it, right? College algebra or intermediate algebra, wherever you guys got this. So okay, so you have, m over s over 1, taking the reciprocal. What do we have? 1 over s. Yeah, so this will result with 1m times 1 is m, s times s is s square, or this can also be written as, I've seen people doing this, and that's fine as well. So it's m over s square or m over s divided by s. All right, so this is your unit for acceleration, 20 meter per second square as an example. But wait, it's not done yet. Okay, every physical quantity is either grouped as vector or a scalar, correct? So let's look at this. So our acceleration is defined as velocity, change in velocity over time, correct? So velocity being a vector, agree? We already seen. Time, we talked about this as well, it's a scalar. So vector over scalar results with acceleration being a vector quantity. Acceleration is a vector quantity. So that means this example here, 20 meter per second square, is incomplete. And then to make it complete, I have to either bring in plus or minus symbol, or an object is accelerating, let's say at 20 meters per second square, to the south. So this here will give you the magnitude part, and of course it has to come with a direction, and this will give you the direction part, making acceleration as a vector quantity. Okay, so let's look at an example for acceleration. Let's say I have an object here, right? And then this object starts to move. So begins to move with an initial speed 2 meters per second. And then, as soon as the object starts to move, I start my timer. So initial information on the timer, let's say it shows me as 0 seconds is where I start the timer from, so that will be my initial time. So this is the object, starts to move, right? Dotted line actually shows you it starts to move, and then it reaches the destination point. And then the final velocity, say 6 meter per second. And then when I check my time, at that particular time, my final time would be 2 seconds. So let's calculate the acceleration. Pretty much, I'm going to go back to the equation form that I had, which said delta V over delta T. So delta V is final minus initial over T final minus T initial. Okay, so V final that we have is 6 meter per second. So minus VI is given as 2 meter per second over, now I have final time which is given as 2 seconds minus 0 seconds, which is my initial time. So that would be 6 meter per second minus 2 meter per second. That will give me 4 meter per second in the numerator, and in the denominator it's going to be 2 seconds. So what do I have? I have 4 over 2 results with 2 meter per second square, or if you would like to write this as 2 meter per second over second. Both are absolutely fine, and this is the acceleration of a given object with the information that's given to us. Acceleration exists only in three different cases: where object is speeding up, object is slowing down, object is moving in a circular motion. But how about if the object is moving with uniform velocity or uniform speed? We have cruise control in the car, and you have that switch which turns on that cruise control, and you, as soon as the cruise control goes on, do you hit the gas pedal or brake? No, right? Object is actually moving with a constant velocity. You're not hitting the accelerator pedal. That means you're not accelerating. Your acceleration is actually zero. So acceleration becomes zero when object is moving with a constant speed or uniform speed or steadily moving. So the last concept that we'll be discussing is the free fall. Now let's say an object which is acting with under gravity alone, right? So in other words, if there are no other forces that's acting on the object, and gravitational force or gravitational pull is the only force that's acting on the object, then we call such objects as freely falling objects. So freely falling objects, let's say an object is falling, right, towards the surface of the earth. Now freely falling object accelerates with a gravitational acceleration. Small g stands for gravitational acceleration, which is equal to 9.8 meter per second square, and sometimes you can see that it's rounded off to 10 meter per second square. Gravitational acceleration is also a type of acceleration, hence comes with the same unit meter per second square. So a freely falling object always accelerates towards the surface of the earth with a gravitational acceleration which is equal to 9.8 meter per second square. Let's say if I have this particular object which is moving right towards the surface of the earth, again accelerating at gravitational acceleration, if I can come up with the speed or velocity with which this particular object is moving given the time, right, different time parameters for us, so that we defined our acceleration as acceleration is a vector and hence comes with an arrow on its head, and sometimes you might see me doing that. So acceleration again is you have change in velocity over change in time, correct? So started off, let's say I'm going to drop an object, right, drop an object, and starting out with an initial velocity of 0 meter per second, and then it gains more speed as it goes towards the surface of the earth. If I expand this, I have change in velocity which is v final minus v initial over t final and t initial. Since this is a freely falling object starting out at 0 meter per second, right, and then gaining speed as it is moving towards the surface of the earth, and also I start out my timer as, let's say, 0 seconds. So that makes our initial velocity, right, this as 0, and then this also as 0 seconds. So that leaves us with velocity over time, right, for the acceleration. Okay, now in order to calculate v, I'm going to isolate, right, v. So that brings us to v equals at equation. I'm going to go with this. For a free falling object, the same equation is written as, in the place of acceleration, we bring in gravitational acceleration times t. So this is the equation that I'm going to go with in order to calculate the velocity with which the object is under free fall. So for this, I'm going to draw this particular picture here. So this is the object which is falling towards the surface of the earth. So this is where our floor is. Okay, so this is moving, accelerating with gravitational acceleration. Acceleration is a vector. Gravitational acceleration is also a vector. Okay, so I'm gonna round this 9.8 to 10 meter per second square, just to make it easier for our calculation. So I'm going to make a table here. Okay, so I have my first parameter t, and then I'm going to calculate v here in the next column. Okay, I'm going to look at various measurements of t. So t is measured in seconds, and then v is meter per second, right? Okay, so I'm going to look at for 0 seconds, and then for 10 seconds, 20, and then 30 seconds. So for all of these time information, I have to calculate velocity. All right, I'm going to go to my equation here that I have. V equals g times t. So I know g, which is 9.8 or 10 meter per second square. So I'm going to bring in that, right? So for t equals 0 seconds, I'm calculating the velocity with which the freely falling object is moving. So 10 meter per second square times time is given as 0 seconds. Anything multiplied by 0 results with 0 meter per second, because second and second cancels out. So if you want to see that more clearly, so this is what I have, times 0 seconds. So second and 1 of the second cancels out. So that still results with 0 meter per second. So that's what we have here. And for the second one, t equals 10 seconds. V equals gt is the equation that we are actually looking at. So we have 10 meter per second square times time information, which is 10 seconds, right? Again, always have to take care of the unit first, second and second. So what do we have? 100 meter per second information. So on and so forth. For 20 and 30, we have 300 meter per second. I'm sorry, 200 is what I meant. And then we have 300 meter per second. And this is how we calculate the velocity information for the freely falling object. Okay, so for a free fall, there are two things that we look at. One is dropping an object. Another one is actually throwing an object. So there are two different free falls. So what happens when you actually drop an object, right? I'm taking an example here. I'm taking a pen and then I just drop it, right? I drop it. So that means I'm not giving it any initial velocity to start out with. I'm not, right? I'm just dropping it. So initial speed for this particular demonstration is 0 meter per second, versus let's say I'm throwing it, right? I'm throwing it. You see, when I throw, I'm actually giving it an extra speed or initial speed. So throw always comes with an initial speed. So same way, see how I'm dropping this. Instead of dropping, I can actually throw. So I'm giving it an initial speed. Multiple different scenarios, correct? So for a free fall, you can drop an object or you can throw an object. The difference is, for dropping an object, there is no initial velocity or speed. For throwing an object, it actually comes with an initial speed. Okay, so let's trace this. You see how when I throw this, let's say it starts out from here and then it moves there. So if I have to show you in this direction to make it a little easier, so it follows a parabolic path, correct? So let me draw that on the whiteboard, makes it much easier. Okay, so here is where let's say it starts out from, correct? And then it follows a parabolic path and then reaches the surface of the earth there. Okay, at this particular point, I'm going to name different points on this parabolic path. The object actually travels through all of those points. So I'm going to call this as point A, and then point B, point C is super important for us. Let me explain that in few seconds. Point D, E, and then I have point F. Okay, so point A, B, C, let's look at that. So I have this parabolic path, correct? So I'm going to take this object through all of those points. Here is my point A, where I'm actually throwing or giving it an initial speed. So it moves through point B, point C. What happens at point C? It loses all the speed. So as it goes through all of these points, the object has to work hard because it's moving against the gravitational pull or gravitational force. When an object moves against the gravitational force, it loses speed. So when it goes through point A to point B, it's actually slowing down. It's losing the speed. And when it reaches point C, the object loses all the speed. So your velocity or speed becomes 0 meter per second, and that's when it changes the direction, moves towards the surface of the earth. And as and when an object is moving towards the surface of the earth, it's actually accelerating with gravitational acceleration. We already saw that. So it is speeding up when it is moving towards the surface of the earth. So let's draw that. So point A is when we threw the object, right? As we throw the object, we give it an initial velocity. So we started out with 30 meter per second, let's say. At point B, we lost some speed. So this now became 20 meter per second. At point C is when the object changed the direction. Velocity became 0, so it stopped moving, right? It vertically stopped moving, and then it started to go towards the surface of the earth. So here we have 0 meter per second, and then I have point D where started to gain speed. So 20 meter per second, and then 30 meter per second, and then reaches point F where it's not moving anymore. It goes to rest. So and then it becomes 0 meter per second. I'm actually missed 2 more points, so I can actually introduce 2 more points here, and then bring in my 10 meters and 10 meters there. Universal understanding, anything which is moving up is moving in positive y direction, right? Negative y, positive x, negative x. That's the universal understanding, and that's what we're going to go with. Okay, so that means at point A it's plus 30 meter per second because it's moving up. That means in positive y direction. Plus 20 meter per second, plus 10 meter per second, and then negative 10 meter per second. Remember, velocity is a vector. It has to have a direction. So negative, because it's moving in negative y direction, negative 20 meter per second, negative 30 meter per second, eventually coming to halt, or velocity becomes 0 at this particular point. Okay, so we have come to the last concept of this lecture. Now we have looked at to calculate the velocity or speed for a freely falling object. Now we are looking at calculating distance that a freely falling object travels in a given time. So for this, let's go back to our original definition of average speed, right? So for average speed, I'm going to write this as v subscript avg. So that means average speed, right? So my average speed, we define this as distance over time. That would be d over t in equation form. Okay, so from in here, if I can isolate d or solve for d, distance would be v average times t. Okay, now let's talk about calculating average, when we have numbers with us, right? So let me give you 2 numbers, which is 1 and 2. How do I calculate average if I have 2 numbers? Very, very super easy. So I add them together. Since I have 2 numbers, I divide them by 2. Let's say I give you 3 numbers, 1, 2, and 3. What do? I add them all and then divide by what? Is it 2? No, right? It's 3 because I have 3 numbers here. So instead of numbers, how about if I give you, velocities or speed, right? So let me give you initial speed and then the final speed. How do I calculate, average speed? If I give you two different speeds, same way, same concept, I'm going to add them together and then divide by, because I have two symbols, two speeds, I'm going to divide them by 2. So this is my average speed, right? So since this is my average speed, I can bring this and substitute that in the given equation. So if I do that, so I have d, which is average speed times d. So in the place of average speed, I am actually bringing in vi plus vf over 2 times t. For a freely falling object, what do we know? Vi will be 0. So substituting that here, so this will be 0 plus vf over 2 times t. And then if I combine all of that together, so I have vf over 2 times t, and then I have d here. So solving for final speed, 2 times d over t, hold on to this equation, call this as equation 1. All right, now going to my acceleration. We define our acceleration as change in speed or velocity over time. Change in velocity is final minus initial over t. Again, for a freely falling object, right, initial velocity is 0. So this is your 0. So you have vf over t. All right, so when you apply this particular equation for a freely falling object where its initial velocity or speed is 0, this equation becomes gravitational acceleration in the place of acceleration, and everything else is exactly same. So you know how we have this final velocity, I can substitute my equation 1 in here. So that would be 2d over t over t. So this is a fraction of fractions, right? So this would be 2d over t, and then take the reciprocal. So that would be 1 over t. When you multiply them together, super simple, this would be t square. What do I have on the left hand side of the equation? So this is your g equals 2d over t square. See that? Okay, so what am I calculating? I'm actually calculating the distance traveled by a freely falling object. So I'm going to isolate or solve for d. So d would be g t square, and then with a reciprocal of half, and that is your equation that we can use to calculate the distance with various time information. Okay, so let's do that. Let's make a table here, right? And then of course 2 rows. My first row with time information given in seconds, and then I have to calculate distance. SI units for distance is going to be meters, so there you go. And then I have various, let's say, come up with 0, 10, 20 and 30, so on and so forth. You can keep continuing, or just look at this for this, different time parameters, and then calculate the distance with, of course, we know g, gravitational acceleration, is 9.8 meter per second square, but then I'm going to round it off to 10 meter per second square. So if I have to calculate, right, for t equals 0 seconds, I know equation to calculate for d. I have this already, right? That equation, I'm going to bring it forward. Half times g t square. Now g we already know, which is 10 meter per second square. I'm going to substitute that just to show you guys how we got the distance information. And then I have time, which is 0 seconds. So 0 square, anything multiplied by 0, we already know it's going to be 0. So distance will be 0 meters. So I'm going to bring in and fill up my table there. So on and so forth. Let's say for 10 seconds, D is half times gt square. So half times g is 10 meter per second square. You see how I'm actually carrying forward all the SI units? Do that, because physical quantity in physics is never complete without a unit. So you always have to take forward the units. And then what do I have? 10 meter per second square, and then 10 second square. Yeah. So half times 10 meter per second square. Look at this, 10 second square. So that would be 100 second square. See that? Okay, so let's cancel second square and second square in denominator and numerator, right? So what do we have? This is your 5. So we are left with 500, and then I have meters here. So 500 meters for 10 seconds. So on and so forth. You can fill in the rest of the table, right? Go ahead, do that, at your, whenever you have time, and then fill that in, and then let me give you the answer and see if you get the exactly same answer. 4500 for 30 seconds. There you go. So what did we do? We just calculated the distance that a freely falling object travels for various time information using gravitational acceleration information, guys. So that's it for today, and I'll see you guys in my next lecture, which would be on Newton's second law. And have a great one. Bye bye.